Hi, David.
Hello.
We're back for another ITOT Insider. Now, before we introduce our next guest, David, you and I have been busy for the last weeks with our third group on the ITOT Academy.
Super cool. And actually, I like it even more this time because, this one is with all the feedback we got from the first two groups.
Thanks for that.
So it's even better. It was already really good, obviously.
No, I have to agree. I really like to see all the interaction of having people from IT, OT together, but also vendors coming maybe more from an IT background to people with a more OT background, and just getting those discussions that in real life don't always happen is very interesting, also for
Absolutely.
us.
So, in any case, here to announce that our fourth group starts in May. We have early bird discounts available. So, for those interested, go to itot.academy for all information. And this kind of concludes the commercial block in this podcast. Hey, we need to make a living as well. So
that's true. So, like I said, we have a new guest today from a very different field than what we're used to, David. Here is Margret Bauer. She is a professor in process automation. Now, I think for most people working in IT and digitalization, process automation is probably like something that's been solved already. Why are we even talking about it? Now, I'll let Margaret explain that in the coming 40 minutes.
Absolutely.
Right,
Margaret.
I'll do my best.
Thank you. Welcome, Margaret.
Yeah.
Thank you.
Thank you for joining us. Hey, let's just, as we always do, introduce yourself. Where do you come from? How does someone become a professor in process automation? And then we can start from there.
So I actually am an electrical engineer by training. So I wish I were a chemical engineer like Willem, but I'm not. I did electrical engineering. I couldn't use much of my degree, actually, 'cause it's all very mathematical. And I did this in Germany. And then I did a PhD in something that was called data analytics, but quite a while back. So started in 2002 and finished in 2005. And I looked at process data at the time. And at that time, it was actually really difficult getting the data from the plant. So I'm talking time series data. I'm talking pressure, temperatures over time that you would get from your automation system. And we'd get it from the data historian. So often you'd have a PI historian at the time or an IP21. And then we tried to make sense with the data. So I particularly looked at plant-wide disturbances. So you, in a chemical plant or in most process plants, you want everything to be nice and constant. So you want your temperature to be at a certain point,
Smooth sailing.
So everything's smooth, and that is the theory. Because practice, if you walk into any site anywhere I've been to, everything's oscillating and fluctuating, and sometimes it's not a problem. Sometimes it's intended. But very often it's something that bothers the operators. And because in chemical plants and in other process industry plants, everything is connected. Things travel through the plant and one affects the other. And then everything suddenly, if you have a disturbance that's oscillating, all your measurements are oscillating. And in my PhD, I tried to find the root cause of such an oscillation. And I developed some mathematical tools, and I felt it was super successful because the code was bought by a company called ABB. And they incorporated these codes into a software product.
Very small niche player in the automation.
Yes.
Never heard of them. Never heard of them.
I suppose this is so funny because we're in the specialist community where we know these companies, but if you talk to anyone in the street, they'll know Siemens because they're household appliances.
Yes,
but ABB, unless you live in the south of Germany or in Switzerland where you have lots of red logos on the highways, on the side of the highways, you probably haven't heard about ABB. So so I have
definitely a big player in process automation for the people who don't know. It's definitely not a small startup that started in 2000s.
So they hired. So I applied my my code to chemical companies, to BP Chemicals in the UK. This is where I did my PhD. I did it with my professor, who's called Nina Thornhill. She then moved on to Imperial College, and she was the ABB professor of process automation at Imperial College. She's now retired, and there's a fantastic colleague who's taking her position. His name is Mehmet Merkangos, and he's continuing her great work. So I applied this to BP Chemicals and to Eastman Chemical Company, which sits in Tennessee. They've got a fantastic controls group there. They call them, I think, the Advanced Controls Group, under a person called Jim Downs. He did this for like 40, 50 years. He's incredibly good. And a super chemical engineer. And I was in this group for a while and applied the codes there. So it was natural to then move on to work for ABB within corporate research. And because I went into this area because I love control. I loved control as a control engineering, as an not control, not like being in control, supposed to, but I love
Other
control.
podcast, other topic.
More
Yeah.
psychology section.
Yes.
Psychology section.
Sorry, wrong
Yeah.
wrong podcast. So I loved control engineering, which I don't know, Willem, you probably had as an undergrad student.
I
Most
think many
engineers,
students, yeah, many
I think,
students have it.
yeah, most engineering students, mechanical, electrical, chemical, they have control systems as an undergrad topic, and I loved it. And when I started with ABB and process automation and in a controls related group, I thought I'm going to do process control, but I didn't. I did ITOT integration.
Ah.
So I tried to connect SAP with ABB's 800XA automation system and I did this. This was in 2007, maybe around that time. So this was cutting edge, like trying to get the two to speak. I had some fantastic, amazing colleagues who helped with that, because as an electrical engineer and doing this kind of thing, I wasn't too comfortable. Just remember, I think it took 3 days to install SAP on a SAP on a computer, and then installing 800XA was another mission, and we had a special computer for that.
It's 3 years to install and 3 days to install and 3 years to configure.
That's fast, David. That's fast.
Oh, that's fast. Sorry.
We had this paper plant. There was like a pre-configured plant which we worked with, and then we managed to send some data from the 800XA to the SAP and back, and we came up with some scenarios where this could be useful, some asset management scenarios, and
I don't know why we're even talking, Dave. I mean, clearly the problem has been solved already 20 years ago. I mean, we've connected it.
integrated.
Let's move on.
Damn, and just today I announced that I was going full time for the ITOT Insider. Is this
Bad idea. It's already solved.
It's a solved problem.
Yeah,
Just like control theory.
Why'd you bother?
Yeah, why do we bother? Yeah, no, that's interesting. But then for some reason, I assume, Margaret, that ITOT side of things that was less interesting for you.
I felt it was a little bit less interesting, and I felt that I didn't. My main concern was that I felt I didn't know about the process industry. So I'd come from academia, and I moved into corporate research, and I felt I'm looking at this data. I don't understand the process underneath. And my PhD supervisor, she said, Margaret, you should do. You should take some courses in chemical engineering so you can understand it better. And I said, no, I was in my 20s, so I was super ambitious. I said, I want to finish my PhD in 2.5 years. I want to set a record, and I did. Why would I take courses? This is going to slow me down. So I was stupid at the time, not taking the patience and not having the patience and doing these courses. So I felt I didn't know enough about the underlying process that we worked on. I didn't understand it, and this is the key actually, because I tried to make sense of the process data. And I looked at the PIDs, the piping and instrumentation diagrams that shows you how everything is connected. And this is important when you have a plant-wide disturbance that travels through the process, and you have to know how things are connected. but it didn't make all that much sense. And then on top of this, the PNID doesn't show you how the connection is between the different sensors through the control layer.
Yeah.
And
Yeah.
this is what I think is the missing layer. No one ever talks about it. And this is what I call the process control layer. And the connection of the controllers lives in it. So how is everything connected? And it's poorly documented, if at all. You can see some of it in the PNID, but often it lives in some code, in some extra code on the automation system.
Maybe for I would say our listeners who come more from the IT side, so a
Right.
PNID, and I also used many of them in my previous jobs, is some kind of it's a plan. It's how do we explain it? It's actually a physical representation of your vessels and your lines and where your sensors are located, but it's more the physical layout, right?
Yes. So it's not not an exact representation, but you have every key equipment, every reactor, every distillation column, every tank. You will have that represented, and then you will have, this is why it's called PNID, piping. You have the pipes that connect the equipment
Yeah.
represented there, and it's in a standardized format, so people can read it. There are standards that describe it. So it's pretty readable, and it's what the process engineers look at when they design the process. Philip, I don't
No,
know.
no,
Yeah,
absolutely. I mean,
so
this is a tool that's used every day. I mean, if you need to
as
analyze what's
yeah,
happening, how do I isolate equipment? How do I what
Yeah.
information is available?
yeah. It's usually very proprietary. So when I did my
Mm,
investigations, it's like as an academic, you have better access to it because you're not the supplier. So as a
yeah.
vendor, as ABB, it would be almost impossible to get access to the PNIDs. As an academic, you have more access because they're thinking, oh, this is Margaret and she's a professor, and who cares? She's a PhD student. So that's even better. and they would share the PNIDs with me after some, often just in paper form, not in electronic form, because
Mm,
people are very cagey about their PNIDs. And very soon you find out that these PNIDs are not accurate. They're not a true representation of the plant because the plants are 20, 30, 40 years old and they have been changed and altered. And no one bothered to implement this in the PNID. And then on top of this, you have your controller structure. So you have this little controller. I don't know how to explain that for the ITOT crowd.
Well, I think you can. I mean, I assume most of our listeners do have some idea of that there's process automation. But of course, there's logic in there. Like
Yeah.
if the temperature goes up, close the valve. Stuff like that
Yes.
needs to be programmed somewhere.
mhm.
And you will not find that program description in your PNID diagram.
Yes, you will find some of it. So there's what people don't, I think, fail to often to realize is there's one control strategy. It has a terrible name. It's the best strategy ever with the worst name, and it's called PID control. And it's so awful. The name is so terrible also because it's so easy to confuse this with P and ID. You think, it's the same letters, only the one has an I. It stands for proportional, integral, and derivative. And if you think that we want to keep a variable constant over time, so we always have this time, we've got time series data, we've got time axis. There's only three aspects of time. It's the present, the past, and the future. So the P part concerns with the present because we're looking at the proportional part, and this is proportional to the current measurement. You have the integral part, which looks at the past, and you have the derivative, which looks at the future. It shows you in which direction we're heading. So there's only three parts to it, and as I say, it's a magical tool, this control strategy. It's completely neglected. People think it's a solved topic, and but the world runs on PID. And I thought I only found this out in the last year or so because I always thought it's the process industry that only does PNID. And I'm sure all these robotics guy and the space exploration guys, etc. I'm sure they have more advanced
No.
algorithms, but they don't. Like 99.9% of all the rockets that have flown into space work on PID control. All the robots, the underlying control strategy is PID. And it is people say that, how complicated can it be? And it turns out it's actually really complicated. And people have neglected it, because when I heard control engineering as a course at the university, I was taught about state space and some very fancy maths and Lyapunov function and Kalman filters, etc. And then was like one half a lecture on PID saying, oh, by the way, there's also PID. And and not explaining. And I think, I don't know, maybe my professors didn't understand that the world turns around PID. It's run by PID. Technology runs on PID control. It's completely underestimated. It's very difficult to implement, by the way.
What makes it so hard to implement?
So the difficulty is that we have physical limitations, and that is mostly the actuator. So what we actually do is, and this is why we're not as fancy as robotics. So everyone loves a robot, right? And it moves around. What we have is, we've got a valve, and the valve will open and the valve will close. And it's just a little, and it opens and it closes. It is not fancy to look at. This is how we work, and this is what we do. We open and close valves in the process industry.
I've never heard of the job description that way, but it's actually quite close to reality. What do you do all day in a plant? Open and close
biggest company, and our products are used all over the world. Your job is
opening
if
and
you
closing
choose to
valves.
accept. Open and close valve.
Well, this is pretty much the process automation job that we do.
There's pumps.
Yes, but the point is all these pumps and there's pumps too. Yes, but most of the time we control with valves, and the point is that these valves are limited, so they can be fully closed or can fully open. So if I compute a control signal that tell my valve, please be 150% open, the valve will say, are you nuts?
It would be very.
I can't do 150%.
It would be great for debottlenecking exercises. So I don't open the valve, 150% problem is solved.
Well, and then you talk about open and too closed. But I've already walked through valves. So you also have the ones who take minutes to open and minutes to close.
Okay, that's a great. Takes me to my next point, which is, so the problem is that we not only have one valve that we often want to interact with, but maybe two valves. For example, if you have a very big valve, you cannot control the flow accurately with a big valve. So what people do, a control strategy that's called big valve, little valve. So you have two parallel flows. One is controlled with a big valve and one with a little valve. And then you have to find a control strategy that adjusts the flow accurately at this very high volume with the two valves, using PID, but finding a strategy that's on top of that. And that's basically controlling, the one gives the set point for the other valve, and the one is always supposed to be 50%. So the small valve strategy is to be always 50% open, so it can react to small disturbances. And the other valve will take care of the big one because it takes so long to open and to close. And so this is called, it's called mid-range control. And my colleague at a chemical company will call it big valve, little valve control strategy. There's different names for it. But this is one of the many control strategies that people use in industry. And these are the strategies that no one ever talks about, that are not documented. And if you don't know about this strategy, you can't make sense of the data.
It's interesting because we're really talking about the low layer control, something which in our ITOT world we don't come across that part of the world, but it's extremely important. Now, having said that, you were still not a professor, because you were working on your PhD, you were working with several companies, and then like at what time does one make the link on I want to teach and research on these topics?
Yeah. So I always wanted to teach and I always wanted to do research. And I started actually teaching in South Africa because I had my kids and my husband's from South Africa. So I moved there during my parental leave. So I actually became a professor there first. And I am now a professor in Germany. We eventually moved back to Germany. I jokingly say, well, if you want to become a professor in process automation, you go and work for ABB Corporate Research, because I have so many peers. I can give you a list of, I think, 20 names easily of former colleagues who are now at different universities across Germany, in Switzerland, in Finland, in the UK. As I said, the colleague who took over from my supervisor, Mehmet, at Imperial, he used to be at ABB Corporate Research in Switzerland. So we have ABB Corporate Research is a very, very special place, especially if you love research. It's the best place to be if you're working in this intersection and if you have an academic career in mind. It's such a beautiful place to be. So many clever people in one building. And so this is how you can enter academia. There are many paths. I have to say, I don't know if you're familiar with the German academic system. So we have two different types of universities. We have the universities that do research, and then we have the teaching colleges. And there's a bit of a hierarchy. When I came back from South Africa, I applied to a couple of positions. I got two, and one was at a very big, very research-focused university, RWTH Aachen, and one was at a teaching college here in Hamburg. And I chose the one in Hamburg because I think if you do process automation, it's a applied subject. I'm at the University of Applied Science. We call this the University of Applied Sciences. And I don't see how I can supervise many PhD students in the subject because it's very difficult to publish in our area. So I basically do my research through master students who are placed in companies.
Okay.
Many of my students have worked before they came to studies. Many worked as operators. And I learn from these students,
Of course.
probably more than they do learn from me. Well, I'd like to think they learn more from me, but I do learn from them a lot because I've never worked as an operator. I don't know what it's like standing there and operating like a metals factory, or I have one student who does a bakery. So he
bakeries, we love those.
I love that, and so glad it's a good bakery because I'm buying that bread. It would have been awful if it'd been a bad bakery, but it's really nice bread that he's doing, and he does per hour about 12,000 bread rolls an hour on his own. So it's pretty awesome. So I learn from my students now.
So we already talked about PID now a bit. What are other process automation concepts people, or at least our listeners, so the ones who are typically not active in the process automation world, should know about?
That's a tough one.
Yes, we are known for our very difficult and
exactly
in-depth questions.
Yeah, so there's a lot of noise particular in the German community, automation community, about different standards on how to arrange assets, and it is not really about. I find this somewhat problematic because it's not really about managing or automating the plant. It's more about managing the assets. So about organizing them, giving them good names, making sure everything's kept up. I never find that very useful when it comes to brownfield, because no one's going to start organizing their assets in a plant that's been there for 20 years. It's just not worth everyone's time. There's no business case.
Yeah, I assume you're now referring to asset administration shell as an example.
For example, yeah. There are a couple of standards. I have just supervised a student on an MTP standard, modular type packaging. And that's, for me, makes sense in the pharmaceutical industry. So that's quite that's very industry specific. I don't see a point I don't see an application in the chemical industry because our plants aren't modular. It's You can't.
No,
It's modular. I
it's
mean, even
It's
my
one big module. It's the plants. There you
yes.
go.
And you wouldn't really connect one module to another module, and today and tomorrow you
You
connected in a different
reconnect your
way.
plants differently. Well, so why not? It's
Yeah.
very
So
flexible.
I work a lot in the data analytics. I love data, I have to admit. So I love looking at data. I love making sense of the data. So the work you're doing is ITOT, having
Mhm.
access to the data is excellent. So I think this is something where we see a lot of progress. I work with a company called Seek. I haven't noticed them on the podcast yet. Have you? You haven't had anyone from Seek?
We haven't got people from Seek, but they are highly welcome to join us. We obviously they are a really known name in the industry.
Yeah. So I've got two super nice colleagues I work with because my students have access to the Seek platform as part of their degree. So I do a course on data analytics, and there we use the Seek platform. And the students can play with it. I think it's very unique because some of my colleagues are jealous that my students have access to it and the others don't. And we do the data analytics, but it makes sense if you're a process engineer. So I teach predominantly process engineers, and it makes sense for them. At the end of the day, it's all about process knowledge. I think understanding the operator's perspective, understanding the process is the absolute key, particularly if you want to make sense of the data, I think.
But okay, so you teach those, but I saw on your LinkedIn feed somewhere a post where you mentioned process control engineers are a dying breed or something like that.
Yes, there are.
Why?
So it's because we automated the automation. That's the reason. So basically, it was a hype topic. I was a professor at Lund University in Sweden for 3.5 years, and I'm still affiliated with them, and I work with the colleagues there very closely. They're the best people working in process control, and one of my colleagues is called Ture Hägglund. Oh, this is where I can point out his book. So if you want to know about process control, can't see this. There's a book. I'm sure you can put
We'll
this in the
link it in the
notes
show notes
later.
as
We're
well.
linking
We'll
Thank
link
for
it
you.
in the
those
show
that want to
notes.
know more about process automation.
Yes, it's very applied. It doesn't have any mathematical equations in there.
How
It is
weird.
just about talking about process control and why it's important. And he's now retired. He's still active. I shouldn't say he's retired because he's still very busy doing research. He's in his 70s, and he's been observing the community for a long time. So he said it was an absolute hype topics in the 1970s, 80s, and 90s, even early 90s. So people got very excited about it. Lots of new developments, MPC, model predictive control, another strategy, got into the area, and it was super exciting. And then what happened was that the process automation worked, and people installed it, and then the companies got rid of their automation department because they said, well, you've automated everything. And
Check mark.
the one exception is Eastman Chemical Company, where they still to this day have this very large control groups. In South Africa, there's a company called Sasol. It's spelled Sasol. In German, we say Sasol. And
Yeah.
in South Africa, we say Sasol. And it's a big chemical company. And they have the highest number of MPC applications in the world in a place called Secunda, close to the Kruger Park. And they have good controls people, but the majority of the companies got rid of their control departments entirely. Some management consultant, like some McKinsey or BCGs or whatever, came in and said, well, you don't need these guys because the process runs smoothly. Why do you need 20 people sitting there? So they got rid of these groups in the 1990s and early 2000s. And the tragedy is in academia, it's not been taught properly. Process control is not taught as a subject. So there's no new process control engineers coming. And now these brownfield plants, they're running, and they're running well, but this is an ongoing, people don't understand that it is an ongoing subject. You can't just optimize your plant and improve it. And so as a result, we see very, very few people doing process control. And I can tell you the academics that work in the subject, and we are a handful in the world, really focusing on it. We're an absolute minority, and we're very passionate about it. But it's a hard battle. Um,
But
yeah.
it's definitely an extremely interesting topic. Yeah, my master thesis was in nonlinear model predictive control.
Mhm.
Um,
Wow. Super.
so and the fun thing is then, well, actually I never apply. Well, that's typically in a master thesis you go a bit to the edge and then you come to the conclusion that let's just take a couple of steps back in reality when
Let's
you
stick to
enter and
spreadsheets.
yeah, not just spreadsheets, but it definitely is a extremely interesting topic. Um, but it also has a downside, in my opinion. Obviously you have less people who are interested in these control strategies, although they are indeed extremely important. But you need to understand the actual process, etc., etc. There is also actually a second downside on the side of the people the operators or technicians who work with the process. Because what I've witnessed, for example, in our past at BASF, was that the more you automate, the more stable your process becomes, the less upsets you have. Also, gives us a positive point from an economical perspective, but a negative point from a personal perspective, that these operators and technicians, they are less exposed to upsets. So you come to this point where you at first you have a good PID control, and then you have a decent SCADA system, DCS system, then you have a decent model predictive control layer on top of that, and then all of a sudden, operators are faced with upsets they don't understand anymore, and then we start talking about operator training simulators, for example. So we're adding another layer on top of that, where we're doing some kind of a flight simulator, but then to train operators, for example, to do a startup or a shutdown or product change or whatever. And it's a very interesting, but I don't know how you look at it from an academical perspective. But
Less
it's a
data
it's a
because there's less variability in the data.
but it's a very interesting thing, where because you also can't say let's turn off the model predictive control layer to make our process less stable again. It's
Yes. Yes. I mean, this all ties in with this, like the latest hype term, which is autonomy. We want autonomous plants, and but it comes to like, exactly down to this. And when I speak to my students who used to work as operators, they said, "Well, I'm not going to work as an operator." That's why they come to see us, because they want to study further, because it's the most boring job. If you have if you have a beautifully automated plant. One of my students said she just took a book with. It's like took a book, pressed a button, sat next to the machine, and then waited. And then 8 hours later, it's like
Shifts
the next
over.
shift came over, shifted, and yeah, she read her book. So it's a fine balance. And then I have other students who reported that um, they get tasks that are, I mean, just to entertain them, just to keep them connected to the process. You know, you walk around, you have a
yeah.
look, you take a reading from a sensor, you look at a pump and check the pump, and you sort of a little bit, yeah, making them work and making them be connected to the process. So it's a fine line. This is what I love about your process, because you say all the time it's about people,
Mm-hmm.
because it's about people at the end of the day. And
Mm-hmm.
I don't think I personally think we'll never be able to fully automate everything. We'll always have a human there because of these exceptions. And you cannot take everything into account, one. And the other thing is all the processes are they're like individuals. Every single process is different, and you're not going to automate that. So we always have a person, and we have to think about it very carefully how we're going to train the operators, how to deal with the operators. I think one key is that it's very easy to find someone who's going to work as an operator, but finding someone who's good and is willing to stay is next
Mm-hmm.
to impossible. And so,
Especially the staying. No.
yes. So, I mean, they go and they move on. They would want to do something different. So you have to think about how to make it attractive, how to make that role attractive, how to challenge people, because it's a very important job. Um, it's, I mean, because you're working close, you have to make sure that it's safe. I mean, often it's not. because you're working close to chemicals that are not good for you as a person, and you can be exposed to them if you're working so close to them. So you have to think about all of this. A lot of them is with people's management, working in shifts, working in teams, setting up these teams. And people have learned, I think, a little bit, but not enough yet, about the people aspect. And that's part of our community. We are all nerdy tech people. I mean, not us, not the three of us, not the listeners.
No.
Absolutely not.
But there are some nerdy tech people out there. And
my wife always
But-
says, David, I refuse to see you as a nerd. You are a geek. That sounds better. I said, whatever works for you.
Well, I have the benefit of being German because Germans don't have a sense of humor in any event. So I could just say, well, I'm not a nerd, I'm just German.
Works.
Mm.
No, so basically you have the automation going so far that's also redefining the job of an operator, actually, and redefining what is a good operator, if I understand you.
Yes. And I think this is where we have to work on. And then also find a place for developing new technologies, because currently I think it's not getting developed. Process automation is stuck. And the reason for this is that no one can actually improve automation because the vendors don't have access to the process. Only with process knowledge will you be able to really improve. But the users are not going to give them that process knowledge. The users don't have control departments anymore. They don't have the experts to improve anything. We're struggling. I don't know if you know about NAMUR, this user association. Is becoming more and more difficult, especially now with the economic downturn. I mean, the chemical industry is struggling. You're not going to build up a group now of process control engineers in this climate, but they should, because then they could develop it further. They could work with the standards. They could make sure it's important to them. But this is not what we're seeing. We're seeing fewer and fewer people being involved from the automation user side. And then you have the system integrators sitting in between, and they don't have an interest either because they're selling at their time, and they can't change the system. So no one can actually improve anything at the moment. So we're sort of completely stuck, it
So-
feels.
Margaret, of course, I'm going to come in with the solution for all your problems. You need to use AI. It's going to solve everything.
It's going to solve everything.
And that's the end of the podcast.
You just need to be more
Okay.
innovative, use AI, and unleash it on the field.
So one of my other master students worked on a reinforcement learning strategy for a batch process. So he optimized the throughput of a batch process for penicillin production using AI. And that worked really well because he had a model of the plant. And this is a model that's out in academia. So in academia, we have a number of processes that are well understood. So one is the Eastman chemical. Sorry, it's called the Tennessee Eastman problem. So you can look it up. It's a paper from the 1990s, a TEP, and it's done by Jim Downs, who I worked with. And people use it all the time to study the behavior in these exceptional situations. So everyone should have a look at this because there's MATLAB code, there's C code available for free for academics online to develop things. And so the other process we have is this penicillin process. And my student developed a really good algorithm using AI, using reinforcement learning, and he could improve the throughput by 25%. Which is magic. It's amazing.
That's a lot.
That's fantastic, but it's all in a simulated environment.
Yeah.
And it's for this one particular process, and
But
it is
you-
not scalable or repeatable or anything.
It's a great point you're making, and that's actually it ties back to the fact that companies are so close about their process models, because we have nearly no access to actual data and actual models. It's extremely difficult to come up with new strategies. When I did my nonlinear MPC thesis, I also tried running it on actual process, and it didn't calculate at all. Just too much too hard to make the calculations. And then I reverted back also to some model I got somewhere with some easy data, and all of a sudden, ta-da,
It comes to life.
it worked. But the problem is that I also knew back then that that way of calculating the optima would never work on actual data. And here we have the same problem, and indeed with AI, and I love the question, Willem, and that's one of the things we have been talking about quite a lot in the last months, is the understanding of the physical twin, the physical assets, the actual process. Well, that is what makes or breaks real AI in a process/manufacturing context. And all the rest is, it's some nice to have, some marginal improvements, but nothing fundamental, I'm afraid. Yeah.
It's what
Yeah,
makes operations also. It's like that links to the physical reality, and every physical reality is different. Even if you have the same plant constructed just next to it, though they will be different. They will be different. You can be 100% sure. You might not know why, though.
I can understand the frustration though, because we are our world is changing. We are in this consumer world where we look at our phones, look at our devices, look at this podcast we're doing now, how easy it is. This wasn't possible 10 years ago. So, we can understand the frustration from seeing how the world around changes and not seeing this change in the process industry and on the side. And I think one has to relax a bit, because the process industry were the first ones that communicated really well. We had all these sensors speaking to each other before we had the internet. So, it's sort of I can understand this. I was equally, when I was working for ABB, I was equally frustrated, because we worked on this project where we had a Google search of the plant. We came up with this Google search using all the data, using this ITOT integration and getting all the data. And then you just search for pump, and whoop, it comes up, and everything you want to know, all the pumps are listed. And then you Google search and you find this one pump, and then get all the information. You get the maintenance manual, and you get all the past data, and you get the vibration sensor data. You get everything together in one spot, and that'd be so amazing. But it's going to be a hell lot of work, and no one's going to pay for it.
That's
so
it. It's an interesting discussion, and it's also a bit more a philosophical one, and we can continue that for a very long time. But I have one final question I'm actually dying to ask you, because I also read that you were creating an art project with control engineering equations. Now,
I might be a customer for that,
Okay.
I would love to have something here behind.
That's the kind of art that I like.
Yeah. Okay, so let me pitch this to you, because I started, and then let me explain. So basically, when I had my kids, I wanted them to be mathematicians, because what's the point of having children if they're not good at maths?
And they need to be mini-me's. That's the whole point.
Great choice.
Exactly,
mini-me's.
That's the whole point. Yeah, I wanted the mini-me's. And then so I read somewhere that your kids are going to be very clever if you play classical music to them. So I bombarded my belly with classical music nonstop for 9 months. And what do I have now? I've got 2 kids who are very good at music and not good at maths. So then we did I participated in this it's called In Control podcast. It's, if you want to know more about control, the In Control podcast is a really good starting point. And the host is called Alberto Paduan, and we did an episode on Sofia Kovalevskaya, who was one of the first mathematicians dealing with control-related topics. There's the Cauchy-Kovalevskaya theorem named after her. And she's an incredible, clever mathematician / control engineer. And so she learned control because she had a wallpaper, because she grew up in Russia and they couldn't afford wallpaper. So they had a wallpaper made out of mathematical sheets. So all the leftover. Wow. So then I thought, okay, clearly the playing classical music doesn't work. But what is going to work is designing a wallpaper made of mathematical equations. It's going to look really beautiful. And then we put it up in the nursery, and you can have a color scheme, choosing different colors. And then all these babies will grow up with these mathematical equations. They become really good mathematicians. So,
Love it.
This
so
is the
I
discrete
started.
mathematics room. That's the statistics room. That's the analytical room. Algebra
So,
room.
so I've got the equations, the control engineering equations together. I started drawing them, and then I ran it past my friends who are architects and PhD in French literature and etc. And they didn't like the idea, and I didn't think my
No.
drawings were
But
very
they
nice.
don't like the idea because they just don't. No. The idea is brilliant.
Well, they didn't like my drawings as such, so I have to. I'm currently working on them. So I've done a first draft, and it didn't hit the spot as much as I liked. So I'm still working. If anyone wants to steal this idea, absolutely welcome. I'm still. I mean, I love drawing, so that's like my favorite pastime is to draw. And so I haven't given up on it. I'm still busy drawing, but it's taking a little longer than I thought it would. But
So
yeah,
let's
we will
maybe then
eventually get wallpaper.
a request towards or an ask towards our audience. If there are people who are really into art and drawing, why don't you reach out to Margret?
I think there's a big overlap between mathematics and art anyway. You'll find also
Should
with
be.
also with music.
I fully agree. I always loved the look of equations, but now we're going
We're going in different. And by the way,
in
I
a
don't think.
wrong direction.
Yeah.
With that, Margret, thank you so much for joining this this podcast. I very, very much enjoyed it. I hope you'll be able to finish the art project, and when you do, let us know. We'd love to be one of your
For
first.
control rooms, we'll put it in control rooms.
Yes, you can put it as your background.
Oh yeah, absolutely.
I can change the poster.
Yeah. Okay, or I can change my
Your globe.
my world map from
Yeah.
1985.
Yeah, it's the wrong projection. I mean, Africa is much too small on that map, so you have to change it in any event.
Yeah. It is, but it's 1985. So
That's okay.
Still has Czechoslovakia.
there are still some countries which don't exist anymore currently. Anyways, again, thank you very much. Also to our listeners, thank you for tuning in. And as always, if you enjoy our content, make sure to subscribe on itotinsider.com or take a look to our academy at itot.academy. Willem, Margret, thank you and see you next time.
Goodbye.
Thank you. Bye.
Bye-bye.